Hey everyone, welcome back to Quick Soil Mechanics Lessons with Brian. This video is Leps for rockfill uses and abuses. So here's the original article, 1970 by Thomas Leps. It's called Review of Shearing Strength of Rockfill. Here's his chart. A lot of us have seen this chart. It's quite interesting. It says that basically the friction angle decreases with normal pressure. You can see very high values on the left side sloping down, high values on the left sloping down to the right as normal pressure increases. It's got a lot of data in there dating back to the 1930s through the mid-1960s. The highest line on there, it says high density, well-graded, strong particles. The next line down says average, and then the bottom says low density, poorly graded, weak particles. So a lot of geotechnical engineers use this average rock fill line for waste rock facilities and heap leach facilities. So let's take a look at that and see what we think about it. There's another guy named Nick Barton who more or less concurs with those findings. He's developed this chart that's on the right-hand side. And on the right-hand side, you can see he's got some other values in there. He's got the R and S values in there, so it doesn't tell us too much. But at the bottom, he says less compacted rock dump materials will tend to have lower R values than the highly packed particles, since there's generally less interlocking. All right. Let's go back to the Leps paper. In the Leps paper, including the closure and discussion, Leps uses the word compaction or some form of it 24 times, and Barton uses it 5 times. So Leps has a conclusion. He says, in summary, all tests on rockfill specimens indicate that the shearing strength of rockfill varies markedly as a function of normal pressure, being high at low pressures and substantially smaller at normal pressures. At normal pressures less than about 10 psi, friction angles in the order of 45 to 60 degrees, with an average of around 50, can be expected when using good quality, clean dumped rock. If excellent compaction is employed, friction angles in the order of 55 degrees can be expected. Now, there's a couple of keys in there. The first one is that it's rock fill, and he talks about excellent compaction. Here's another chart by Barton. It's kind of a confusing, very busy chart. You can see that he's got this R value running across the top with those slanted grid lines. He's got other lines crossing through there with the origin, roundness, and smoothness, and on the bottom is porosity. So he says the high porosities in mine rock dumps clearly places such dumps in the middle to right-hand side of the diagram, and even sharp angular particles are likely to generate R values, are unlikely to generate R values above about 5 to 7. Okay, so far. So that doesn't mean a whole bunch to us yet, because we don't know where in the chart we're going to be, but we've got this chart that plotted several different waste rock types with density versus effective stress and providing void ratio. So let's just add into there, knowing our formula for porosity. And so we can put these porosity values into there. So we know that on the loose end, the porosity is somewhere around 0.3, 0.333. So we can chunk that onto this chart over here. And we fall somewhere around here. At the bottom, we've got this formula that Barton gave us for underlying shear strength. And then in there, you can see this R value. So the smaller that R value is, the lower the shear strength is going to be. And here we're talking about some pretty small R values compared to what's on the chart there. So The right-hand side of the chart has got a 5, and that's where that red circle sits. So that gives us a little bit of guidance here. Let's take a look at this again. So as it says here, unlikely to generate R values above about 5 to 7. So this is the different chart. This is the one that was presented earlier. So let's see what this does to us. Well, here's an R of 7.5, so it doesn't show us anything down to 5 to 7. But you can see that friction angle on the right-hand side, if we've got some parallel or some sub-parallel line to this below there, it's not going to go up to 50 degrees. It's going to be underneath there somewhere. Right. And just as I said, under that 50 degrees somewhere. Okay, so let's look at the Corps of Engineering design and construction for earth and rock filled dams. They give this big statement here. They say that rock fill should not be placed in layers thicker than 24 inches. So we don't do that on heap leach facilities, and very seldom do we do that on a waste rock facility. So those are probably not getting qualified as rock fill. And here they talk about smooth wheeled vibratory rollers having static weights of 10 to 15 tons. Definitely don't do those on normal waste rock facilities, and certainly not heap leach facilities. USDA in their earth fill and rock fill book, they say rock fill, once placed in the required lift thickness, is best compacted by heavy vibratory compaction equipment. Earth and rock fill dams book provides us with this handy dandy table, and up at the top it talks about layer thickness for uncompacted layers. Here we've got actually rock fill, and they say 60 to 150 millimeters, so 0.6 to 1.5 meters. So that's a little bit thicker than we're talking about, but much less than we normally work with in heap leach and waste rock facilities. So those facilities generally don't correspond to rock fill, and that's what Leps has given us information for. So let's look at this. This is a angle of repose slope on a waste rock pile, and you tell me that that material somehow has say a 50-degree friction angle on the outside of the slope. So let's talk about angle of repose and angle of friction. Those two parameters are equal if the loosely packed material is consolidated. So the material on the outside of the slope is not consolidated. So that material on the outside of the slope it doesn't correspond to its friction angle, at least not yet. So why did Leps and Barton find such high values of friction angle for rock fill, especially at low confining stress, so much higher than their angle of repose? Well, because the rock fill was compacted. So this is pretty complicated to think about. Why do these guys tell you that the friction angle is higher, so much higher than the angle of repose, or what you might get in your triaxial shear test? Well, the shear strength of the material that are at low effective stress have been compacted in those experiments, the rock fill, and their frictional behavior mimics fill that's at a much higher confining stress. So that's how you get that 50 or 55 degrees at low confining stress, is that it's been compacted as if it's been subject to a much higher confining stress. And those lines in, say, the Leps chart slope down to the right because as their burial depth increases, effective stress increases eventually to a point where the effects of compaction are no longer evident. So we kind of get back to its normal friction angle, which is close to the angle of repose. So that is a lot to think about. Okay, now, should we use Leps for rock fill or for waste rock facilities and heap leach facilities? Probably not without thinking about it really hard. I think it's better to use Barton. He's got some more testing that needs to be done, but it is very useful, and I think it can be put to good use. So coming back to this chart here, you can see those high friction angles at low confining stress, like we just went through. That's because it's been compacted as if it's been buried very deeply. And that high friction angle disappears as it becomes very deeper and deeper so that it goes back to its normal friction angle like you would see close to the angle of repose. Well, that's a lot to think about. It's been a long video, and this is a good time to end it. Hope this helps people to understand it and appreciate it a little bit more before you just mindlessly go about using Leps for your analyses. So till next time, hey, hang in there. It's going to be okay.